Hello, welcome to this video. In this video, let us learn about working of Otto cycle and then let us derive efficiency equation for Otto cycle. Now, the Otto cycle is an idealized thermodynamic cycle which describes the functioning of a typical petrol engine, or what we call it as spark ignition internal combustion engine. Remember, we are talking about 4-stroke engines. That too, particularly in this class, we are talking about petrol engine, or what we call it as spark ignition reciprocating internal combustion engines. All right. Now, before we start our derivation, I think we must know the basic terminologies which we use in our IC engines. There is a piston and a cylinder arrangement, and there are one inlet valve and outlet valve. Okay, here it is represented as valves, and then there is piston here which moves within this cylinder, and there is extreme position of piston, we call it as top dead center here. All right, and extreme position on the towards the right side, we call it as bottom dead center. So, piston moves from top dead center to bottom dead center, and the volume which it covers from TDC to BDC, we call that as swept volume. All right, and in 2 dimension it is called as stroke length, in 3 dimension it is swept volume, and the diameter of the cylinder we call it as bore, and the volume which is left behind this piston even when the cylinder touches top dead center, we call that as clearance volume. All right. Now, very important, we have learned top dead center, bottom dead center, swept volume, clearance volume, cylinder, piston, bore and valves, and it is very important that there is a design parameter which we call it as compression ratio. Now, many use this compression ratio by a different terminology, but let us keep it as R. R is our compression ratio. All right. Now, what is R? Compression ratio is something like what was this total volume of charge which is our air which is taken in. So, if this is our total volume, right. So, this is our total volume. So, when valve is open, this much of air or charge is taken in, and how much it is compressed to? It is compressed till here, till clearance volume. So, compression ratio here will be what was the total volume. Now, total volume will be clearance volume plus swept volume. So, clearance volume plus swept volume divided by clearance volume. So, this will be our compression ratio, and this is very important design parameter because we derive our efficiency in terms of compression ratio, because this is what will be in the designer's hand, right. So, we can decide on compression ratio, and we will later see how compression ratio affects the efficiency. So, this total will be Vc plus Vs. So, compression ratio in a typical petrol engine will be of the order 8, 6 to 8, whereas in diesel engine it will be little higher. We will discuss that later. Now, let us come back to the working of 4-stroke petrol engine. All right. Now, there will be 4 strokes as name suggests, and there is ignition by spark. Okay. There has to be a spark plug which ignites the fuel and air mixture, and the fuel used is petrol. Now, remember there is an intake valve. I am looking at the intake stroke here, the one where the suction is happening, right. Now, suction is happening because as the piston move downward, there is a pressure drop within the cylinder. Okay, there is a pressure drop within the cylinder, because of which, since the inlet valve is open, the charge, and very important, the charge comes in. Charge means fuel plus air which is already mixed in the carburetor. So, fuel plus air is the one which is coming in. So, when intake valve opens, the exhaust valve will be closed during the intake stroke. Piston moves from top dead center to bottom dead center, and air fuel mixture is drawn into the cylinder. So, mixture is what is coming in inside the cylinder. Okay, and piston moves from top dead center to bottom dead center. All right. Now, during compression stroke, both the valves are closed both the walls are closed, and whatever the charge is here inside is compressed from bottom dead center to top dead center. Now, air fuel mixture is what you are compressing. Okay. Now, this is compression stroke. Then power stroke is where when both walls are closed and then spark plug ignites this mixture. So, remember we already have air fuel mixture which is drawn in, it is compressed, and now we are igniting it by a spark plug. The moment it is ignited, we can see that burning mixture expands, all right. The combustion products expands, because of which it pushes the piston from top dead center to bottom dead center. So, piston moves from top dead center to bottom dead center and it produces power. That is what all we wanted. And in the last stroke, that is exhaust stroke, we are at bottom dead center now, and the moment we execute this power stroke, the exhaust valve is open now, and during that exhaust stroke, piston moves from bottom dead center to the top dead center, moving the or pushing the combustion products or gases outside the cylinder. So, this is how a typical 4-stroke petrol engine operates. And remember, this rotation for a 4-stroke engines, it is like for each stroke it will be, for each stroke, that is for suction stroke this will rotate 180-degree, for compression stroke this will come back here, so 180-degree. Okay. So, for each stroke the rotation will be half. Okay. So, therefore, the total rotation will be for 4-stroke, the total rotation will be 720-degree. So, 180 plus 180, 360 and 360 here. So, for every 2 rotation, we will have 1 power stroke. That is why we also call it as, I mean, we can write 4-stroke petrol engine like this. 4-stroke engines are like, for every 4-stroke, there will be 1 power stroke. That is also we can define in that way, or in terms of rotation of the shaft also we can write it like, for every 2 rotation of the shaft, we will have 1 power stroke. So, both are valid. Now, let us try to write PV and TS diagram for a Otto cycle. Okay. Now, I have taken this, retained this 2D diagram where we were trying to show the terminologies used in Otto cycle. So, we will go for Otto cycle efficiency. So, PV diagram. Now, let us try to recall the strokes. Now, suction stroke, right? Suction stroke is where piston is moving from top dead. I am just have oriented the cylinder in horizontal direction, that is it. Okay. So, I will start from somewhere here, the point, because this is where our clearance volume is. Remember, I am trying to replicate the same volume, or trying to show the same volume which is here by this point, all right. So, clearance volume is here. So, piston is starting from here during suction stroke. Now, what happens during suction stroke? During suction stroke, piston moves from top dead center to bottom dead center. So, piston is moving from here to here. Both the I mean inlet valves is open, whereas exhaust valve is closed and piston is executing suction stroke, which means piston is moving from top dead center to bottom dead center, during which what happens is that because of the pressure drop, the charge comes in, okay, because of the pressure drop. So, I will call this as 0 and let us say it comes to here, right. I mean the working fluid will be here. I will call this as 1. Why are we starting it from 0? I will tell you. Okay. Now, actually the pressure drop happens and it is recovered by the charge coming in. So, in reality it will be something like this: pressure is dropped and it is recovered as the charge comes in, but that cannot be idealized, or we cannot analyze that process unless we have something which is easier, because we have ideal process like constant pressure, volume and so on. So, this cannot be solved, this cannot be analyzed. So, we will assume that the pressure remains constant during this process, that is an assumption. So, pressure remains constant during suction stroke. So, this is our suction stroke actually 0 to 1 is our suction stroke. Now, I can write that 0 to 1 is suction stroke. Now, what we will do is compression. Now, compression is both the walls are closed. The same diagram you can we can think of. In the same diagram, compression stroke is where now we are here. It has to come back to initial state, all right. But pressure will be higher. So, we are compressing the charge. Now, how do we compress it? Now, let us assume the compression stroke is reversible adiabatic compression. So, we are trying to establish an ideal cycle which replicates the working of petrol engine or spark ignition engine. So, reversible adiabatic compression, reversible adiabatic compression. So, that is an ideal process for compression. So, 1 to 2. So, 1 to 2 is reversible adiabatic compression. Now, what happens is the moment we are here, we have executed suction stroke, piston moving from TDC to BDC. We have now compressed from bottom dead center to top dead center. Okay. Now, both the valves were closed during this process. Now, we provide this spark at this point. Now, the moment this spark is given, it is very important. This is what makes a distinction between Otto cycle and diesel cycle. The moment spark is given, the fuel is already homogeneously mixed during in the carburetor itself, and that has come in. The moment ignition is given, at a given instant of time, within a small amount of time, or even when the piston is there only, the combustion occurs. So, we are assuming that heat addition is in fact, we are during a standard assumption we have made it clear that heat is supplied from outside. So, it is assumed that as if the piston is at that fixed position only, the heat is added. So, it is an assumption that heat addition happens at constant volume. Now, this is why heat addition is at constant volume in Otto cycle. So, 2 to 3 is not a stroke actually, it is heat addition at constant volume. So, piston is there only, but the moment the spark is given, the heat addition occurs. Now, 3 to 4, now because of the expanding combustion products, the piston moves from top dead center to bottom dead center. Now, 3 to 4 again we will have to come back from top dead center to bottom dead center, but we are coming with a process which we called as reversible adiabatic expansion. So, that is an ideal process for getting the work done. So, reversible adiabatic process looks like this in a PV plot. So, 3 to 4. So, this position I am trying to keep it same, right. So, because piston is moving from here to here, but the pressure and temperature within the cylinder or the pressure and temperature of the air may be different. Now, from 4 to 1 is again, now 4 to 1 is again what will happen now, exhaust valve has to open and piston should move from bottom dead center to top dead center. Now, the moment exhaust valve is open, most of the energy within this combustion products or most of the gases which is inside the cylinder moves out of the cylinder, which means as if the piston is here only, we are assuming that the heat is rejected. Okay. So, at constant volume heat is rejected here. So, that is what is the assumption. At constant volume only, heat is rejected again. Now, this is where heat is rejected. This is where our heat is supplied. Okay. Now, 4 to 1 is heat rejection at constant volume. Heat rejection at constant volume. And remember, we are still have not completed the cycle yet. We are here. The moment exhaust valve is open, most of the combustion products rushes out of the pressure difference, all right, because of the higher pressure inside the cylinder and outside pressure will be atmospheric. Most of the combustion products rushes out, and that we are idealizing it as constant volume heat rejection. So, this is our PV power gamma is equal to constant. Okay, this is also our PV power gamma is equal to constant. This is our volume constant. This is volume constant. Okay. Now we let us execute the exhaust stroke. Now, exhaust stroke is again whatever combustion products which is left inside the cylinder as piston moves from bottom dead center to top dead center, it keeps on pushing out. So, it does not let the pressure to rise, but as the piston moves from here, the moment pressure is happening, it is pushing out the combustion product. So, it is like constant pressure. So, we will come back from bottom dead center to top dead center on the same line of 1 to 0. So, 1 to 0 is again constant pressure. So, which is nothing but exhaust stroke, which is nothing but exhaust stroke. We can readily eliminate these two, because if you try to work on these two, they will cancel out. I mean, if you try to do what work done during 0 to 1, if it gives some value, and again if you are pushing this backward, it will take the same amount of work. So, in technically if we speak, we need not to consider 0 to 1 and 1 to 0, because they will cancel out, all right. So, Otto cycle, many people start from here simply 1, 2, 3, 4 and 1. So, that is what is necessary. We just gone beyond and try to explain that the strokes are 0 to 1 and the exhaust stroke and suction stroke can be eliminated. Now, 1 to 2 is compression, 2 to 3 is heat addition, 3 to 4 is expansion, and 4 to 1 is heat rejection. Now, we are ready to go for efficiency of the Otto cycle. Now, how do we start? Efficiency is given by work done divided by heat supply, desired output divided by heat supply. Now, work transfer is what? We can write it like heat supplied from first law of thermodynamics, Qs minus Qr by Qs, or we can also write it like 1 minus Qr by Qs. And now remember, we have already used this negative sign. So, while substituting, we do not want the equation to be negative. We will make sure that the equation has to be positive. Now, for constant volume, which we have already discussed in the last class, that for constant volume it has to be heat transfer is given by mCV dt, all right. Heat transfer is mCV dt. So, heat rejection is mCV, heat rejection is happening between 4 and 1, and to keep it in positive, all you have to do is highest minus lowest. Now, temperature versus entropy diagram also we should have drawn, because temperature is what we can estimate here. Okay. So, let us try to write TS diagram here, TS diagram for the same cycle. All right. Now, temperature versus entropy diagram. I am completely neglecting 0 to 1 and 1 to 0, even though they are strokes. We can readily neglect, because they do not give us any work or they do not absorb any work, because they will cancel out, all right. So, 1 to 2 is reversible adiabatic or entropy constant. So, we know how it looks like 1 to 2, and 2 to 3 volume constant. We have discussed volume constant looks like this in a TS plot, that we will have to remember, so this is entropy constant or PV power gamma constant, both are same. And then 3 to 4 is again isentropic. So 3 to 4 is again isentropic, and then 4 to 1 is again volume constant. This is volume constant. Okay. Now here we can see now MCV QR is here, right? I mean between 4 and 1, between 4 and 1. So this is where our QR is, this is where our heat supplied is. Now highest minus lowest is what we need to do. Now if you see here the temperature plot, this is our highest temperature, this is our lowest temperature. Alright, T4 is highest, T1 is lowest. So I just want to make sure that we are substituting positive here. So MCV T4 minus T1 divided by MCV, heat supplied is between 3 and 2. So it is T3 highest minus lowest. So MCV cancels out. Now all we have is that efficiency equation is 1 minus T4 minus T1 divided by T3 minus T2. So this is our equation. I will call this as equation 1. We will come back to this equation 1. We are interested in representing temperature in terms of compression rate. I mean efficiency in terms of compression ratio, because efficiency I mean compression ratio is a important design parameter. Now how do we come to that? Let us consider process. The idea is here to eliminate temperatures and write it in terms of compression ratio. So idea here is eliminate temperature. So now how do we eliminate temperature? T4 if you write it in terms of T3, T1 in terms of T2, we can eliminate that. I mean you can cancel the numerator and denominator, and somewhere we will write it in terms of compression ratio. Now how do we write this in compression ratio is of importance. Let us start doing that. Now process, let us consider process 1 to 2. Process 1 to 2. Now what is process 1 to 2? PV power gamma is equal to constant, correct? Now PV power gamma is equal to constant means I can write P1 V1 power gamma is equal to P2 V2 power gamma. Actually I am interested in temperature, not in terms of pressure. So I will try to eliminate pressure. So this we have done earlier also. PV is equal to MRT I will use. In place of pressure I can use MRT by V. So in place of pressure I can use MRT by V, but here temperature I mean MR will get cancels out. So I will not use MR, I will write T1 by V1. In place of P1 I am using T1 by V1. V1 power gamma is equal to T2 by V2 power gamma. Okay. So T1, if this goes to the numerator it will be minus 1, and if you add the power it will be minus 1. T2 V2 power gamma minus 1, or we can simply write T2 or T1, I will write it like T2 V2 by V1 whole power gamma minus 1. Now what is this V2 by V1? Let us check. Now V2 is what? V2 is here, that is clearance volume. Okay. Now V2 is equal to V3, same, correct, is clearance volume. All right. Now V1 is actually total volume, right? I mean clearance volume plus swept volume. Okay. So now we know compression ratio is given by Vc plus Vs by Vc, which is nothing but V1 divided by V2. So compression ratio can be written as V1 by V2. Now we have V2 by V1, I can write T1 is equal to T2, this is 1 by R. So that will be 1 by R power gamma minus 1. Okay. So, I am intentionally writing this R this way because we do not want to get confused with R and gamma. Okay. So, that we will have to take care. Now, let us do the same thing on the other side. So, we have represented, so intentionally we have done this T1 in terms of T2 I have written. Similarly, can we do the same for T4? Now, let us go for T4 means process 3 to 4. Similarly, let us do this for process 3 to 4. So, for process 3 to 4, so process 3 to 4 is PV power gamma is equal to constant again, and we know 3 power gamma is equal to P4 V4 power gamma, and we are substituting this PV is equal to MRT equation same here, and in place of pressure we can write T by V, and we say that then T3 by V3, V3 power gamma is equal to T4 by V4, V4 power gamma, and we have T3 V3 power gamma minus 1 is equal to T4 V4 power gamma minus 1. I will check. We are interested in writing T4 in terms of T3. So, I will retain this T4 on one side. So, T4 is equal to T3 V3 by V4 whole power gamma minus 1. I will check what is V3 and V4. Now, V3 is equal to V2. So, again we have V3 by V4 is nothing but clearance divided by total volume Vc by Vs. I mean Vc by V1. So, this will be again T4 is also equal to T3. Now, V3 is our clearance volume, V4 is our V1 because V3 is equal to clearance volume and V4 is equal to total volume V1. So, therefore, is nothing but V2 by V1. Okay. So, V1 by V2 is R, whereas V2 by V1 is 1 by R. So, T3 divided by R by gamma minus 1. So, T4 also we have written in terms of T3. Now, substitute these two in equation 1. Substitute, I will call this as 2 and 3. Substitute 2 and 3 in equation 1. Now, efficiency is equal to 1 minus, in place of T4 we have T3 by R for gamma minus 1. In place of T1 we have T2 by R power gamma minus 1. So, denominator is there only as T3 minus T2. Okay. So, 1 minus this term. Now, I will take efficiency is equal to 1 minus, I will take T3 and T2 common here. Okay, sorry, I will take 1 by R for gamma minus common here. 1 by R for gamma minus 1 common here. I will be having T3 minus T2 in the numerator, and denominator we had this T3 minus T2. This was the whole idea of substituting this in T3 and T2. So, these two will cancel out and we will have efficiency is given by 1 minus 1 by R power gamma minus 1, where R is compression ratio. Compression ratio is equal to V1 by V2, where V1 is total volume clearance plus swept volume and V2 is clearance volume. Okay. So, we have represented efficiency of an Otto cycle in terms of very important design parameter, that is compression ratio. Let us derive a mean effective pressure of an Otto cycle in the next class. Thank you.